What is up, everyone? It's Miss Wesley, excited to come back and talk to you a bit more about binomial probability distributions today. As you're turning to page 19 of your statistics packet, I have a quick question for you. Did you guys hear about the bedbugs who fell in love? Oh, yeah, they got married in the spring. Today is a perfect day to practice some more now that we've introduced the concept of a binomial probability distribution. And what you'll see all over page 19 here are a bunch of situations where what are those common properties? You'll see a fixed number of trials in the experiment. You'll see two possible outcomes. One thing will happen or another thing will happen with this constant probability of success because the trials are independent of one another as well. The top of this page, man, it makes me think back to the good old days of the Philadelphia 76ers, and I looked it up. Embiid is making 83% of his free throws currently, with trials being independent. What's the probability he makes 6 out of 10, at least 6 out of 10, and less than 6 out of 10 free throws? Give this one a try. This is great practice to solidify yesterday's skills. 6 out of 10, that sounds like one specific case. In my calculator, I'm going to use that shortcut, a binomial probability distribution function, PDF. And 6 out of 10, that means we have 10 trials. We'll call n 10, and it's always n comma p, usually comma x when you're using a PDF. So probability of success is his 0.83. A higher probability than I have at free throws. We want to know the probability that he'll make 6 of those 10. So that should be the setup there too. We'll walk through it on the calculator real quick. We'll remind ourselves where we found that binomial PDF, and it was at second and the vars key for distribution. You got to go scroll all the way down to letters A and B are what we're going to use today. A is for PDF. We have how many free throws out of 10, which would be our n. He makes 0.83. I'll just put 0.83. And we want to know the probability that he makes 6 of those 10. That should do the trick. Enter with the commas there, and you get a 0.0573. Over these pages, in general, nearest thousandth is going to be okay. A lot of times you'll see me putting 3 significant digits on these answers too. So sometimes I'll put nearest 10,000th. This one's a 0.0573 if you're interested in 3 significant digits. This is almost going to be a rare event. It's greater than 5%, so it doesn't quite make it into that category of being statistically rare. What's the probability that he makes at least 6 out of 10? This makes me think, this at least, makes me think we're adding up a few cases, right? That he makes 6 free throws, 7, 8, 9, or 10. So instead of adding up a bunch of PDFs, an at least could be a 1 minus a CDF. 1 minus a binomial CDF. C standing for cumulative distribution function. Still 10, still probability of success of 0.83, but I want to subtract off all the cases up to 1 less than 6. I want to subtract off that he makes 0 shots through 5 shots from that total of 1. So I'll go to the calculator, type it in, 1 minus a CDF. 1 minus, same menu, second in vars for distribution. We'll say binomial CDF, which is going to be letter choice B down here. And then the same n value and the same p value. So we'll say still 10 trials, still probability of success of 0.83, and then we want to add up to 5. That's what we're subtracting off. Should do the trick. A 0.983, pretty good odds of that happening, about 0.983. Then we look down to number 3 where it's asking what's the probability he makes less than 6 out of 10 free throws. That makes me think of just a straight CDF, 6 or less than 6, so that would be 5 or less if you think about it. So I want to take a binomial, since we want to add up cases here, binomial CDF. Let's less than 6, well we still have 10 trials, and a 0.83 chance that he makes the free throw. That's going to be adding up the cases that he makes none, 0, 1, 2, 3, 4, or 5 would do the trick. If you pause the video and type this in, see if you get, check your answer with this, 0.0168. And really, I'm not so sure I did this one the quickest way. Think about it. Either the case of number 2 is going to happen, he makes 6 or more, or what's the probability he makes less than 6? That would be the other percentage of the time. I could have just taken this answer and subtracted from 1 to get this solution. If I add these up, add these 2, you get a total of 1. That covers every case. All right, so we're still talking about Embiid, but let's just say It's the end of a game. Things are getting exciting. He's fouled as the time expires, and he goes to the line to attempt 2 free throws. Let's find 3 different probabilities for 3 different outcomes for the Sixers. What's the probability? Now, it looks like each of these is going to be a PDF. He makes both free throws to win the game. So binom PDF of how many trials does he have? He only gets to attempt 2 this time. N is going to be 2. His probability of success will still say his statistic is a 0.83, but he wants to make both of them. So that's all 2 of them. This would be a straight PDF at 2, and type that into the calculator. Go ahead, check it with mine, and you'll get a 0.689. So I like those odds. I'm already feeling pretty comfortable because almost 70% of the time, he's just going to outright win the game at that moment. What's the probability he makes one or the other, just one free throw? Well, this is good with the PDF as well. Binom PDF. Almost the same exact setup, right? He's going to the line for 2 shots. He's got this probability of success, but we want to know the odds that he does make one or the other. Then he makes one of those 2 shots. Type that into the calculator, you get lower odds, 0.282. So a 28.2% chance the game goes into overtime. There is the other possibility, and as a Sixers fan, we know this could happen. What's the probability he misses both? A binom PDF. I'm still going to say he has 2 shots, and it's a 0.83 chance of success, but he's going to get 0 shots in, causing the Sixers to lose the game, and this is a slight 2% or 3% chance, 0.0289. Like that. So all 3 of those, I didn't see at least, at most, I didn't see any instance where we're adding cases together. So no CDFs required in 4, 5, and 6. A few more examples here. The statistic is that 9% of men and 0.25% of women are actually colorblind and cannot distinguish between the colors red and green. This causes problems with traffic signals because, you know, green, red, and yellow are what comes on a traffic signal. If 6 men are randomly selected for a study, find the probability exactly 2 of them cannot distinguish between red and green. I see that exactly 2. I got to decide PDF or CDF. I'm thinking binom PDF. It's one case that we care about. What's your number of trials? You are randomly picking 6 men. The probability that they cannot distinguish, I'm going to say the probability of success here is that they are colorblind. So I'm going to say P equals 0.09. Like that. And that'll be what I call success in my experiment. So a 0.09 could go here for men, 0.09. And what's the probability exactly 2 of them turn out to be colorblind? I'll put a 2 in there for my X, for my desired number of successes. Go ahead, pause, type that in, and we'll round this to the nearest maybe 3 significant digits. Your calculator should give you 0.0833, like that. So you have an 8.3% chance that 2 of those randomly selected men won't be able to distinguish between the colors red and green. 6 men are randomly selected, same exact setup, at least 2, right? This makes me think of 1 minus a CDF. So one way to do this would be 1 minus binomial cumulative distribution function, CDF, still 6 men, still a 0.09 chance that they are colorblind, at least 2, right, would be 2 or 3 or 4 or 5 or 6. We're subtracting off a CDF up till 1 less than 2. 2 minus 1 would be what I plug in for that last slot, so we subtract off the cases of 0 and 1 being colorblind. Try to pause, type this into the calculator, use a CDF this time, and maybe check your answer with mine. I got a 0.09. So a slightly higher answer than you got for number 7 because you're adding a few more cases to that answer. The Telectronic company purchases large shipments of fluorescent bulbs and uses this sampling plan. They randomly test. They get a huge shipment of thousands. They randomly test 24 bulbs, and they'll say, oh, the whole batch is good if they only find 1 or none that don't work. I want to show you a few. There's a lot of ways you could show your work for number 9, a lot of good ways to get this one into the calculator. If a particular shipment of thousands has a 4% rate of defects, what's the probability we will accept this shipment? So we have to write a binom PDF or CDF for the probability that, let's think about it, out of the 24, either they're all good or only 1 isn't good, and we would still accept it. So I'm going to say 23 or 24 are good. like that. So I got to think to myself, I could actually just add up two PDFs. This wouldn't be a bad idea. A binom PDF of how many are we testing? Out of 24, the probability that the bulb is good, if it's bad 4% of the time, it should be good. We should be able to say 96% of the time. So 0.96 would be the probability of success that a bulb is good in this case, that 23 of them are good, plus add the case binom PDF that 24 are good, 0.96, 24. Add those together. Feel free to pause so that you can get that typed in. But add those together. The number to check it with is going to be 0.751. And I'll show you one or two other ways you could show this work. Another way you could do it, right? Or another way to think about it. You could do probability that 0 or 1 are bad. Like that. Where we call P the probability of success actually being bad, not good. So 0 or 1, let's add them up. A binom PDF that out of 24, the probability of it being bad is a 0.04 chance. Add a 0 case, and then to a binom PDF to a 1 case. 24 bulbs, 4% are bad, and then if 1 is bad, we still accept it. Check that one, because if you type it in, you should still get 0.751. Like that. And then in case we needed it, and we really don't, a third way that you could show it, out of many ways, this could also be a binom CDF. So I'll say binom CDF. So this is one way, this is a second way, this is actually a third way. A cumulative distribution function for 24. Probability of them being defective is a 4% chance, and then putting a 1 there. If you go CDF and you put a 1 here, it does what we did in blue a bit quicker because it'll add up the 0 case to the 1 case. So for this one, you should be able to check and get the exact same thing, 0.751. So 3 different ways to all arrive at the same conclusion. At the bottom, an article stated that internal surveys paid for by directory assistance providers show that even the most accurate companies give out wrong numbers 15% of the time. So there's our percentage that's advertised. Suppose you're testing such a provider by making 10 requests. Looks like we have an N value of 10. Also assume the provider gives the wrong number, the wrong telephone number, 15% of the time. So we have to decide how we want to set this up in terms of what we'll call P. And I'll call this a wrong number is going to be my success, actually. So wrong number 15% of the time. Find the probability of getting exactly 1 wrong number. To me, that's 1 case, and it looks like a PDF. So I'm going to say binom PDF, 1 wrong number. So out of the 10 that I'm testing, I get a wrong number 0.15 of the time, and I want to get the case that there is 1 wrong number. Go ahead, type that in. Feel free to pause, and I'll round it to 0.347. 34.7% of the time that's occurring. How about an at most one? We haven't seen this in a little while. At most one, remember, CDF is made for this situation because at most one would be, what's the lowest? 0 could be wrong or 1 could be wrong. This is kind of like the last question. So for an at most one, let's do binom CDF. Let's say we're still testing out 10. We still get a wrong number 0.15 of the time, and we want at most 1. If we put a 1 here, that'll add up the cases of getting 0 or 1, and we see what that comes out to be. So you get a pretty high percentage. You get at most 1 wrong number, 0.544, above half of the time is going to be your probability. A little bit of interpretation at the bottom. If you do get at most 1 wrong number, does it appear that the rate of wrong numbers is not 15% as claimed? Well, actually, this case in number 11 seemed like it happened a bunch of the time. I'm going to say no to this one, and I'm going to say there's a good chance. There is a good chance. That good chance we found in number 11, 0.544, that you get at most 1 wrong number. So I'll say of getting at most 1 wrong number. If the rate is actually 15%. So I'll trust it. I like those odds, and I hope you enjoy the rest of your day in this practice with binomial probability distributions. See you soon.